Good morning, everybody who is here. Welcome, welcome.
Morning.
Um, did everyone get the recording and key for yesterday's exam review?
Yes.
Perfect. Sorry I had to end it a bit early. We had to take off from here, so we are good to go this morning, though. Is everybody okay if I start with going over activity group work 10, I mean?
Yes.
What everyone wants to go over first? Okay, let's do that. So, was there specific questions that anybody had on group? Oh, this is group work 9. Let me see. Not this one, right?
That's actually the right one. This one is labeled group work 9, but it's group work 10.
Group work 10. Okay.
Yeah.
Perfect. So, what questions do you guys have specifically? Do you just want me to go over all of it? Certain questions?
For like 1 and 1B. So I know that like since there's a BR group, it pulls the parts per million downfield.
Yeah.
But is there? I probably just missed it, but like, is there a specific amount it pulls the hydrogens downfield? Like I know a methylene group is usually at 1.3 if it's connected to 2 carbons.
Let's
So does it?
go to the chart that he's going to provide you on your exam. Okay.
Okay.
So here's the chart. Let's see, HNMR. Okay. When you have a halide or a halogen attached, it's going to be anywhere from 2.5 to 4.5. Do you see this right here?
Yeah.
Halogens are represented by Z, so it's anywhere from 2.5 to 4.5. Having 2 bromines will probably pull it towards the 4.5 number rather than the 2.5.
Okay.
So, on number 1.
Let me write that down real quick. Sorry. Okay, thank you.
Yeah. So the same with not part B, except chlorine's going to pull harder than the bromine, so it'll be a little downfield than the first one, is what I would guess. But let's double check. I brought the key up too. We can double check. Oh, that's right. And also, do you guys see there's 2 different hydrogens? Because it's on a double bond, the chlorine is going to pull the HAs further downfield than HB. And it looks like in the first one, it's about 4.5 as well, HA in the first one. So, cool. Sorry for the background noise. All right. Any other questions?
Are you okay with just like, I don't know if this is what the other people want you to do, but would you be okay with just going through like the whole packet?
I can work on that with you guys. Whatever. Yeah. I'm here for you guys. You got your exam tomorrow, so whatever you're most worried about. So, all right. So we have identify A and B isomers, the molecular formula C3H4Cl2, the given HNMR data. So compound A exhibits a signal at 1.75 as a doublet. It's got 3 hydrogens and the J value 6.9. We don't need to worry too much about the J value. Okay. So what I would do on this one is I would draw out an HNMR graph for A and B. And then we want to figure out what the formula is going to be, what the compound will look like based on those HNMR graphs. So let's go ahead and draw A. Okay, so 1.75, we have a doublet. So you guys can remember this is 1.75. We have a doublet, and there's 3 hydrogens there. Okay. Then we have at 5.89, sorry, we have a quartet, which is 4, and there's 1 hydrogen there. Okay. So that's our H&MR graph, rough. I'm having to draw with my finger. I apologize, so it's not working out great. Let's try to figure out what the molecular formula would be here, or the compound would look like. So what I like to do is I just like to start with my carbon chain, okay? And then I say, all right, we have 2 chlorines to add, and we have 1 hydrogen with 3 neighbors, and we have 3 hydrogens with 1 neighbor. So what I would think that means is that we would have probably like a chlorine like this. Let me think. If we did that, then there wouldn't be another peak, another signal. Let's think through this. Does anyone have any ideas?
So I got like a carbon with 2 chlorines coming off of it, double bonded to another carbon. If that makes sense. I know that's kind of hard to.
This?
Yeah.
We got our 2 chlorines. We have 1 hydrogen with 3 neighbors, 3 hydrogens, and we have 1, 2, 3, 4. Perfect. Yep. So that's what that compound's going to be. That's A. Cool.
Is there a way, like I really struggled on this one, because of the double bond. Is there a way to know that it has a double bond?
Yeah, so you can do degrees of unsaturation formula.
Oh, okay, cool.
Yep, use that formula, and it would tell you that if it has 1 degree of unsaturation, you're gonna have 1 double bond. If it has 2 double bonds, and so on.
Okay, and that can be applicable for any NMR data, right? Like with if we're given the right stuff.
Yep. If you're given the chemical formula, you can find out how many degrees of unsaturation.
Cool.
So let's do B now. So we've got a signal at 4. Okay, 4.16, and it's a singlet with 2 hydrogens. We also have one at 5. 5.42, it's a doublet with 1 hydrogen. Okay, so 1 hydrogen with 1 neighbor and 2 hydrogens with 0 neighbors. Okay, so again, start with our base formula here, and then probably what it's going to be is, let me try this. Chlorine that has 1 hydrogen, and it's going to be a double bond as well, because we know there's a degree of unsaturation. It's probably going to be like that. Let's see, 1 hydrogen with, no, that doesn't quite fulfill it.
I think we still have a 5.5 doublet as the last peak for this.
Oh, yeah, that makes sense. I didn't see that last peak. Sorry. Am I okay to draw this first compound, or erase this first compound?
Yes.
Yeah.
Just give me a bit more space. Then we have 5.59, our other 5. It's a doublet with 1 hydrogen. Perfect. Sorry, I didn't check that out. Thank you. So that helps out as well. So let's see, 1 hydrogen with 1 neighbor. So maybe the double bond is on the other side. Because if we had chlorine, that would be 2 hydrogens with no neighbors. And then, yeah, because those are on a double bond, yep, that's going to be it. Is that what everybody else got? Because these are our 2 hydrogens here. These are 1 hydrogen with 1 neighbor each. They're neighbors to each other. And then this is our 2 hydrogens with 0 neighbors. Everybody okay with that?
Yeah.
Cool. So that's kind of the thought process that I go through. I just kind of like manipulate the molecule as I go along, try to figure out exactly what it's going to like.
Have you found it helps you to draw like the carbon chain first?
I always do that.
Okay.
And if I have the chemical formula, I usually will use the degree of unsaturation formula.
Okay.
Yep. Just to make sure, hey, I know I've got a double bond in this molecule, so I always account for that early on. So I'll draw my carbon, add the double bond somewhere, add all the other stuff, and then I figure out, if that fulfills it or not, and then I adjust as I need to.
Okay.
Can you explain what the degrees of saturation means? Because I used the molecular formula provided in this question, and it came out as 3. I don't really know what that means.
Okay, let's double check it. I can't even remember what the formula is. Can someone read it to me?
Yeah, okay. So the HDI equals 2C
2C, so we've got 6, okay,
plus 2
plus 2
plus N.
plus, what is it?
N.
N is
We don't have any, I think.
hydrogen, or nitrogens, yeah. So no nitrogens.
Minus H.
Minus H. So we have 4.
Minus X
And we have 2 chlorines, so we have minus 2
divided by 2.
divided by 2. Okay, so 6 plus 2 is 8, minus 4 is 4, minus 2 is 2 divided by 2 equals 1. 1 degree of unsaturation.
So does that mean there'll be 1 double bond?
1 double bond.
Oh, all right, thank you.
Yep. Any other questions?
Nope.
Cool. All right, let's do this next one then. How many CNMR signals will be present in each of the following compounds? Has he gone over CNMR yet?
Kind of.
Kind of.
Yeah.
I know it's tough. Summer classes, it's like, it doesn't feel like it, but yeah, technically he like mentioned it for a second,
Yeah.
How many CNMR signals will be present in each of the following compounds? The most important thing is to determine, it's kind of like HNMR. You find out, 1, if there's a plane of symmetry, and 2, if the carbons will be identical to each other, okay? So this first one, let me just zoom in a little bit so we can see it better. Okay. So we've got 1 carbon here, 1 unique carbon. We have a second unique carbon in the middle, and then all 3 of these outside ones are all going to be different from each other. Okay. So, or sorry, they're going to be identical to each other. So we have 1, 2, 3 CNMR signals. Okay. It's not a huge portion of the exam, the CNMR stuff. It's kind of like it's not super helpful to understand. I mean, I guess, but HNMR is more helpful in my opinion. CNMR, but so it just tells you how many different types of carbons there are in the molecule, and this one has 3. Okay. Let's look at this next one. Now there is a plane of symmetry here. Okay. Goes right here. I know it doesn't kind of really look like it, but those bonds can rotate, and so basically there's 3 carbons on this side, 3 carbons on this side, and a double bond in the middle. So that's what makes those identical. Okay, so you're gonna have 1, 2, 3 signals for this one, and they'll be identical 1, 2, 3. Does that make sense?
Yes.
Perfect. This next one, there's a plane of symmetry up the middle. So we've got 1, 2, 3, 4 different signals. This one will be identical to that one, this one identical to that one, so we get 4. Okay. These 2 will be identical, so that's 1, 2, 3 signal. Any questions on how we got those?
Nope.
All right, got the IR CNMR of molecular formula C6H10, proposed structure for Y. Okay, so let's first look at the IR spec. What is this 2120 going to be?
A triple bond between carbons.
These are our sp3CH bonds. And then this is our sp-CH bond. Okay. Then the CNMR, we know that there's 5 signals. Okay, so we'll just make sure that we get 5 signals from our CNMR. Okay, so we've got, I'm going to start with my carbon chain, 6 carbons. And we know there's a triple bond. Okay. We've got 1 hydrogen, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's make sure there's 5 different signals, carbon signals.
I think there might be an extra carbon.
5. There should be 6 carbons. 1, 2, 3, 4, 5, 6.
Oh,
Okay. Now let me think. So we have too many signals for our CNMR. So how can we resolve that? Any ideas? Isopropyl, perfect. That's what I would recommend. Okay, so this will create, oops. Okay, that'll create these 2 signals to be identical. So 1, 2, 3, 4, 5. Okay, so that will be our molecule now. Any questions on how I got that?
could you explain about terminal?
Yeah, so terminal alkenes and alkynes, okay, that just means that they're at the end of a carbon chain. So this C triple bond C is a terminal alkyne. Whereas if you had this molecule, let's say, right, this would be an internal alkyne, this would be a terminal. Does that make sense?
Yeah. And how can we tell on the IR?
Because this peak shows up. Oops. This peak. That's your sp-CH bond. If it's an internal alkyne, there will be no sp-CH bond.
Oh, I see.
Because it's this hydrogen on the end that causes that peak.
Gotcha.
Yep.
Cool. Thank you.
Cool. Any other questions on this one? All right. Identify the compound with molecular formula C8H10O that gives the IR and HNMR below. Okay. So you got a 1600. What does that tell us? Yep, perfect. C double bond C. Okay, if it was closer to 1700, it would be C double bond O. Okay. Then we've got 2850, which is our sp3CHs, and 3100 is our sp2CHs. Okay, and that comes from our double bond. So now we got to look at our IR spec. We've got these hydrogens down here. What does that tell us? Between 6.5 and 8. Anyone remember?
A benzene ring.
Perfect. What type of benzene ring? Mono or di-substituted?
There's 2, so a di-substituted.
Di-substituted, right? Because there's 2 and 2, which gives us 4 hydrogens around the ring. So that's going to be a di-substituted benzene ring. Okay. Whoop. Okay. And then we know that there's going to be 2 things on here. We'll just draw like that for now, okay? So you know it's a di-substituted benzene ring, and these 4 hydrogens are going to be these 4 right here, okay? And what makes them split is depending upon what, what type of groups you have on either side of the ring, but you don't need to know the difference there. Okay, so we have our C double bond C's taken care of. We have our sp3 CHs, we have our sp2 CHs, we have our benzene ring. Okay, so now let's look at our HNMR here. Okay, so we have 3 hydrogens with no neighbors, and we have 3 hydrogens with no neighbors here. Okay. But we need to find out what our formula is, because we have to account for an oxygen and 8 carbons. Okay, so right now, how many carbons do we have? We have our 8, but we still have an oxygen to take care of. Okay, so let's try doing like a ether. Okay, so we'll go with something, an ether group. Okay, we still have 8 carbons, and we have our 3 hydrogens with 0 neighbors, 3 hydrogens with 0 neighbors. Okay, does that fulfill our chemical formula?
Yes.
Yep.
Perfect. I didn't know. I was just trying stuff. Okay, because we knew we didn't have a double bond O, and we didn't have any alcohol peak up here, right? Because if there was an alcohol in it, it would be something like that, right?
Mm-hmm.
So that's why I said it's not going to be a double bond O, it's not going to be an OH, so I figured let's put an ether and try it. And that does fulfill our formula, so perfect. Any questions on how I got that?
Nope.
Perfect. So shown below are the HNMR spectra of 2 constitutional isomers. Determine the structure of these compounds and label appropriate peaks. So we know they're both C9H12, but they have different connectivity, okay? So let's figure out what this is. What does this tell us right here?
Benzene ring.
Perfect. What type of benzene ring?
Monosubstituted?
Perfect. So we know there's going to be one thing attached, okay? And we need to have 9 hydrogens, 9 carbons, and 12 hydrogens. So right now we have 5, 6, 7, 8, okay? And only 7 carbons. Let's just do something like that, right? Okay, so now we have 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so our chemical formula is fulfilled. Let's see if our HNMR matches. So we've got 1 hydrogen with lots of neighbors and 6 hydrogens with 1 neighbor. Ooh, what does that tell us? That's one of the ones I went over yesterday. Yeah, isopropyl, right? Whoops. Why does it keep doing that? Let's get rid of this. Okay. I don't know why my computer's wigging out right now, but okay. So let's look at that. So 1 hydrogen with lots of neighbors, 6 hydrogens with 1 neighbor. So that is fulfilled. Perfect. So that's our first molecule. Everybody understood how I got that?
Yes.
Yep.
Okay. So let's look at this next one. What does this tell us? Right here.
Another benzene ring.
Another benzene ring that's monosubstituted, right?
Yep.
Okay. And then, so we can just start with that. All right. So now we've got 2 hydrogens with, it looks like 3 neighbors.
Yeah.
You agree, 3 neighbors there? Okay. And then we've got a multiplet with 2 hydrogens, and it looks like another 3 hydrogens with 2 neighbors. Okay. So what does this tell us? When we've got 2 hydrogens with 3 neighbors and 3 hydrogens with 2 neighbors. What does that tell us?
They're next to each other?
Well, let me think. Yeah, it's kind of tricky to see how many peaks are in each of those. Trying to see.
So I thought that was a triplet, the one at like 0.9.
So that would be 3 hydrogens with 2 neighbors, you're saying?
Because didn't you say that was a doublet?
Yeah, I think that's 2 neighbors with 3 peaks, right? It's gonna be a triplet. So I mean,
Yeah.
2 neighbors there. Okay, and then I think the 2 hydrogens on the far, like the left, and I think that's a triplet as well. Or does anyone see that as a quartet?
I think that's a triplet, yeah.
Let's see. Between. Oh, you know what? It is a triplet. It's right here. It's showing them.
Yeah.
Yep. So that's a triplet as well. So 2 neighbors, 2 hydrogens, 2 neighbors. And then 2 hydrogens with 1, 2, 3, 4, 5, 6, 5 neighbors. I'm just going to write those numbers in while we're thinking about them, okay?
Yeah.
So I think that's all that's going to be is just a carbon chain because
Yeah.
You got 2 hydrogens with 2 neighbors. These are 2 with 2 neighbors, 2 hydrogens with 5 neighbors, and 3 hydrogens with 2. Yep, that'll be it. Perfect. Sorry that took me a minute to get there.
Those peaks are so hard to read sometimes.
Yeah.
Like,
If they're hard like this, he will give them zoomed in.
okay.
So I wouldn't stress too much. Or either that or it doesn't matter. You don't need it to solve the problem or whatever. So
I got you.
cool. Okay, carrying on. This is a long group work.
Yeah, it is.
Holy cow. All right.
Okay, you picked yourself.
So we want to identify the structure of the compound from the following spectroscopy information. So now we have 3 graphs here. What's this top left one?
Mass spec?
It is the mass spec. Perfect. So what's the mass of our molecule?
57?
Someone said 57. What did the other person say?
86.
86? Okay.
Odd. Damn. Okay.
Mass is going to be the furthest right one. So that's right. It is 86.
Oh, okay.
57 is the, oh my gosh, what's it called? The ion peak or something like that? Does anyone remember?
Parent base peak.
Base peak, that's what it's called, yeah. Yep. 57 is the base peak. It's the one that's the tallest, and that's basically when the molecule gets shredded. That's the most stable mass. That's essentially what that means, but it's not too important as far as trying to find out what the structure is. So we know our molecule weighs 86, okay? We have a peak at 1710. What does that tell us?
C double bond O.
Yep. Perfect. And what is our 2950?
sp3ch.
sp3s. Okay. All right. So it looks like we have 2 hydrogens with 3 neighbors and 3 hydrogens with 2 neighbors. Okay. All right. So now we know we have a C double bond O. Our molecule needs to weigh 86. And we have not a crazy amount of hydrogens, to be honest. Okay, so let's start with roughly how many carbons do we think we'll have? Our thing needs to weigh 86. We know oxygen weighs 16. So let's take that out, 70 roughly. So
4 or 5?
5? Let's start with 5. I have no idea. We're going to start with 5. Okay. So 1, 2, 3, 4, 5. Okay, we know we have a C double bond O. I have no idea where it's going to go. I'm just going to put it here in the middle. Okay. The reason I did that is I'm looking at our HNMR and I'm saying, well, we only have a few peaks, right? So we almost need it to like have a mirror image or something like that. I'm not sure if that's going to fulfill it, but we'll check it out. Okay. So now we have 1, 2, 3, 4, 5, 6, 7, 10 hydrogens, 1 oxygen, and 5 carbons. Let's see if that adds up to 86. So we have carbons equal, we have 5 carbons, so that's how much? 5 times 12. 60. We have oxygen, which is 16. We have hydrogens, which are 1 each, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's right. Okay. So does this add up to our 86?
Yes.
Perfect. All right, so let's see if it fulfills everything else. We accounted for our C double bond O. We have sp3 CHs. We have our total mass. And yes, it does fulfill our HNMR. So that is our molecule. Cool.
Derek, I just had a question. So obviously I need to go over mass spec again, but you said the furthest right peak is the molecular weight?
That's going to be your molecular weight.
Okay, thank you.
Ones to look out for, if your molecular weight has 2 peaks, like if there's 2 peaks at the end, and they're separated by 2, and they're a 1-to-1 ratio, what does that mean is in our molecule?
I have no idea.
Does anyone remember? So let me say that again. You've got 2 peaks at the far right of your mass spec. Yeah, perfect, Tanner. So 2 peaks at a 1-to-1 ratio that are 2 apart. That means there's a bromine in the molecule. Okay, how about two peaks at the end at a 3-to-1 ratio that are 2 peaks apart? Chlorine, perfect. So just watch out for those. I can kind of draw what those would look like. So chlorine, it would look something like this, right? You'd have a tall peak and a short peak that are 2 apart at a 3-to-1 ratio. Okay, that would be a chlorine, and then a bromine would be, you got your mass spec, and they are the same height, so 1-to-1 ratio, 2 apart. That would be bromine. Just a little, remember there. How about if your mass spec is odd? What does that tell you? Is in the molecule.
Nitrogen.
Nitrogen, perfect. All right, let's do this next one. Identify the structure based on these graphs, okay? So what is our molecule weight here?
59.
59. All right, what did I just say?
Nitrogen?
Yeah, we got a nitrogen, 59. Okay, we got a nitrogen. Okay, we've got our sp3s. And what is this 3400? Does anyone remember?
Amine.
Yeah, it's an amine. Let's go check out our graph here, right? So HNMR, IR spec. We've got right here, between 33 and 3500 is your amines. Perfect. Okay. All right, and how many peaks is it?
1.
1 peak. So what does that tell us?
Primary.
Primary amine. Let's see. It's actually a secondary amine. It's going to have 1 hydrogen. Okay, so if you see here, this NH, okay, that's in secondary, and that's 1 peak. Because when there's 1 hydrogen, that means the nitrogen is bonded to 2 carbons.
Uh-huh.
Okay, so it's a 1 degree amine. Okay, so let's go back up here. We have a, so let's see, 1 peak is a secondary amine. Come on. Perfect. Okay, so now let's look at our HNMR. We've got 1 hydrogen with 0 neighbors. Okay, and what's the, what are the ones we know between 4 and 5? Let's go look at our HNMR thing here. Between 4 and 5, what do we see?
Vanillic. Vanillic.
It's either going to be vanillic. Let me think. Could be an oxygen as well. Anyway, we can worry about that in a minute. We'll just take a look at what we got. Okay. Not exactly sure. The graph didn't give us much info there. Okay. So we've got 2 hydrogens with, it looks like, 3 neighbors because it's got a quartet. Do you agree?
Yes.
Yeah.
3 hydrogens with 0 neighbors. And 3 hydrogens with 2 neighbors, it looks like.
Yeah.
Okay. All right, so we know we have a secondary amine. We know our mass is 59, and we have our HNMR. So let's go ahead and start with a carbon chain. So what do you think? Should we try 4 this time? Oh, let's see. That might be too many still.
3.
Let's try 3. Okay. So let's try that. And then to have a secondary amine, I'm going to add the nitrogen right here. No, that's not going to work. Let's put it in the middle. Let's do something like that. So that's, oops. Okay, so that's still our 3 carbons, our 2-degree amine. Okay. Now we've got this hydrogen right here. Could be our 1 hydrogen with no neighbors, and it's also bonded to a nitrogen, which would make it very deshielded, so that's matching up. Okay. We've got 2 hydrogens with 3 neighbors, so that works out with one of ours. We've got 3 hydrogens with 2 neighbors and 3 hydrogens with 0 neighbors. So I think that's our molecule. What do we think?
Yep.
Yep.
Do you agree? Cool. Nothing too crazy, right?
Nah.
Oh, let's make sure that's our mass too. So we got carbons. We have 3 of them, right? So that's going to be 36. We've got nitrogen. Anyone remember how much nitrogen weighs?
14.
It's 14. And, or sorry, 15.
15.
What did you say? 13?
I think 15. 14.
Is it 14?
Yes.
Number. Okay. And hydrogen. 3, 4, 5, 6, 7, 8, 9. Does that up to our 59?
Yep.
Yes, it does. Perfect. All right. Sorry, I just wanted to make sure we had it good there. All right, so we want to identify the structure of the unknown compound based on the following spec. So same type of problem, okay? What do we see in our mass spec?
1-to-1 ratio.
BR?
Yes, we have a 1-to-1 ratio with 2 peaks. Okay, so we know this is going to be a BR, and our mass is going to be 108. Okay. We've got not really a whole lot in our IR. We know we just have sp3CHs. Okay. And then we've got 2 hydrogens with, it looks like 1, 2, 3, 4, 3 neighbors. Do you guys agree?
Yes.
3 hydrogens with 2 neighbors.
Yep.
Yeah.
And then that peak down there is solvent, so we don't need to worry about that. Okay, so let's try to put our info together here. So does anyone know how much bromine weighs?
79. Or is it 81?
What does it say on Google? Because it doesn't account for the
Yes.
80?
79.9.
89.9.
79.9?
Basically, yep. Okay. Carbons. So since we know bromine weighs 80 and we're only going to 108, I would say probably 2 carbons. Do you guys agree?
Yes.
24. Okay. So what that would look like is we'd have our 2 carbons and then a bromine. Okay. And that would give us 3 5 hydrogens. Does that get us to our 108?
Yes.
Somewhere in there. it doesn't matter a whole lot as far as bromines and chlorines go, as long as you're within that range right there. Perfect. So I think that's correct because we have 3 hydrogens with 2 neighbors, 2 hydrogens with 3 neighbors. I think we're good to go. Any questions on that one?
Nope.
All right. I want you guys to walk me through this one. I think this is our last one, right? Yeah. So I've given you kind of my work through on this. You guys talk me through this one. Okay.
All right.
What's our mass?
58 grams
58.
per mole.
58 grams per mole. Perfect. What else do we see in our IR?
There's a carbon double bonded to oxygen.
We saw that in the chat as well. C double bond O. Okay, what else in our IR?
sp3ch.
Perfect. sp3s. Okay. Not a whole lot else in our IR. What about our HNMR?
A singlet.
Okay. We have a singlet with no neighbors. Okay. Okay. What else do we see in our HNMR?
Another singlet.
Okay. Got solvent. Yep. And I'm not really sure because that's at 0, and there's nothing that's really at 0 in HNMR, I don't think. We can double check. Okay, so kind of a crazy looking one, but let's just try to put all of our information together, see if we can come up with an answer. All right.
All right.
How many carbons do we think?
2.
2?
3.
Okay, we can do 3. What do you guys want to do? We go with 3? Let's do 3.
Sure.
There's our 3. Should we add our double bond O?
Yes.
Do it. You want to put it in the middle or on one of the sides?
The middle.
Okay. If we put it on one of the sides, it would make an aldehyde, and that would show up in our IR. So I agree with that. Okay. So let's check our mass right now. Let's just see where we're at. Okay. So we have carbon. We had 3, right?
Yes.
Hydrogen, we have 16. And right now we have 6 hydrogens. Does this add up to our 58?
Yeah.
Yeah, it does. Perfect. So our mass works out, okay? This peak right here could be 3 hydrogens. It didn't give us the information, but that would be consistent because these hydrogens are identical to each other, okay? So it could be a total of 3 hydrogens there that are all identical. Okay.
So
No.
that's not a typo. Like that can show up on the exam where like there's just a singlet with no like 3 hydrogens attached to it.
Yeah, so he may show it like that because you didn't need to know any more information. All you needed to know was there was only one type of hydrogen, right?
Okay.
So he didn't need to put that there was, 6 hydrogens in that peak, or that there was, he didn't need to give you any more information. So that's really,
Yeah.
So I think that's it. Everybody agree?
Yes.
Yeah, perfect, Lynn. That's right, because it gives one signal because I didn't. Awesome. And that's it. Perfect. Any questions on any of those?
I have a question, but it's not a specific problem here. It's just like a general question about singlets.
Go ahead.
All right. So I was going through your exam review and the key as well. And it was like one of the problems identifying whether it's a singlet, doublet, or whatever neighbors it has. And my question is, are all like OH, the H, identified as singlets?
Yes, because you can't go through oxygen to find neighbors.
Oh, thank you.
Nitrogen. Mm-hmm. Oxygen and nitrogen are unique. They can't have any neighbors. Those hydrogens attached to oxygen and nitrogen, you can't go through there. Even if they're within 3 sigma bonds, you can't go through oxygen and nitrogen to find neighbors.
All right, perfect.
Yeah, I'm glad we went over that. So, because I'm sure some people didn't realize that. Yeah. And I'm sure Dr. Gard mentioned it briefly in one of his lectures, but it's so it's so quick over the summer. It's like just a whirlwind. So it's hard to get all those little rules and details. So glad we talked about it. All right. Well, I'm here for you guys. Do you want me to do a couple of examples of like some substitution reactions? Do you want me to just go over the rules of those quickly? Do you want me to go over any other topics on your exam? I'm here for you guys for the next 15 minutes.
I think I'm good, but thank you, dude.
Yeah, no worries. Glad you can make it.
Can you scroll back up to the beginning of the page
Yeah, sure.
real quick? Check this.
I didn't actually draw number one, if that's what you were wondering. Do you want me to draw it?
Yeah.
Sure. So your part one on question one, you're just gonna have when something is attached to a halogen. Let's go double check the graph so you guys can see it as well. Okay. When it's attached to a halogen, it's somewhere between 2.5 and 4.5. Go back up. And the difference between the first one and the second one is that chlorine is going to pull harder than the bromine. And also because it's a chlorine and a bromine, those two are going to show up differently on the second one. But it's just going to be a singlet. Whoops. Sorry. My computer keeps wigging out. Okay. So BR, they're going to show up as a singlet between 2.5 and 4, I said, right?
Yeah.
So we'll just do something like this, right? And that'll be HAs. Okay. Whereas on the second one, so are those going to show up as the same hydrogens or are they going to show up differently?
Different.
Different, right? So we're going to have a doublet, right? Somewhere in here. This will be our HA, HB, okay? And our HA is going to be less de-shielded than our HB because the HB is going to get pulled harder by the chlorine, right? So it's going to be slightly more de-shielded, and they are doublets this time because HA and HB are neighbors of each other.
Okay.
And the reason they're different is because they're on a double bond. Anytime carbon or hydrogens are on a double bond, they're different from each other.
I just put. I mean, I put that, but I put them in the wrong spot.
Oh, you're good.
So,
And I say anytime they're on a double bond, if the other side of the double bond is identical, they're the same, like in the first example. But because most of the time molecules are going to be different on each side of the double bond, that's what makes them different. But like in the first example, the BRs are identical, so that's why they're the same. Cool. Anything else? You guys all okay on the substitution reactions?
Yeah.
Okay. Well, if nobody has any more questions, we can finish it there.
All right. I have a question about your answer key.
Yeah,
Because I think you circled the wrong answer for your exam 3, second to last page.
Let me pull that up. You said the second to last problem.
Third to last problem.
Which one here? Consider the rate.
Yeah.
Okay. Consider the rate of the following reaction. What would happen to the rate if you double the concentration of both, you know, your ring and your OH?
Yep.
So what is this, SN1 or SN2? You guys can see.
True.
SN2. Why is it SN2 though?
the nucleophile is a very strong.
Yep.
one.
Perfect. So we have a strong nucleophile, and SN2 prefers strong nucleophiles. Okay. So we have SN2. What is the rate dependent upon, or what is the rate in SN2?
Second order.
It is second order. So you have your halide and your nucleophile. Okay. So if you double the concentration of both your nucleophile and your alkyl halide, then you're going to times 4. Oh, sorry, answer the wrong one. Yep. I did circle the wrong one. It is quadruple.
All right.
I apologize. Any other questions? I think I did put my summary on here as well of substitution reactions, SN1, SN2.
Yeah, it's helpful.
Yeah. Oh, perfect. Here you go. Yep. So what I did, this is just my brain. When I took the exam, I memorized this list, and as soon as the exam started, I went and wrote it down immediately. I just wrote down SN1, 3 degree, 2 degree, rate is this, 2-step or also stepwise. I memorized and I just wrote it down really quickly at the beginning of the exam,
Mm-hmm.
just so I could have something to double check my thinking on everything. But so this is a good summary of SN1, SN2 reactions. Awesome. Any other questions? All right. We'll end it there for today. Thanks for coming, everybody. Good luck on your exam, and we'll talk next week.
Thank you. Have a nice vacation.
Thanks. We'll see you guys.
See ya.
Bye.